Let's talk about the mechanism for adding water, for hydrating an alkene or adding water to an alkene. Now, the reaction is acid catalyzed, right? Let's remember what a catalyst does. A catalyst will speed up the rate of a reaction by decreasing the activation energy, but always remember your catalyst does not get used up in the process of the reaction. It's regenerated, okay? And we're going to show that in this mechanism, all right? So let us use one propene. We're going to react it with water. I have water in blue and my acid in red for specific reasons, right? Then we regenerate the acid at the end. When you write reaction mechanisms, your strong acid, such as H2SO4, is represented by the hydronium ion H3O plus. This reaction actually has three steps, right? In step one, your first step, your alkene is going to react with the acid. We can either look at this reaction as a proton transfer, where the alkene gets protonated, right? Or you can look at it as a new bond between a nucleophile and an electrophile. I think I'm going to use the latter. So the usual, whenever you have a reaction, you need to find your source, which is your nucleophile, rich in electrons. That's a double bond. Pi bond is rich in electrons, that's your nucleophile. Then our electrophile is the hydrogen, right? The hydrogen is the sink, so this will act as our electrophile. So we're going to make a bond between the nucleophile and the electrophile, or if you want to look at it as a proton transfer, it is the same thing. So remember, we draw the tail of our arrow from our source to our sink, right? From your source to your sink. And what this line is telling me, what this arrow is telling me, and let me move this down so I can just write what the arrow really means. So the arrow is telling me, if I could get to move this down, the arrow is telling me that the double bond is going to break, right? Leaving me with a carbon-carbon single bond. Let's just move part of it and then rewrite the hydrogen. Okay, so the double bond is going to break, leaving me with a carbon-carbon single bond. So I like to write at the top what the arrow means. So this arrow, right, means I'm making a bond between one of these carbons, right? The red hydrogen is going to add to one of these carbons. This reaction follows Markovnikov rule, okay? So the arrow is telling me that one, the carbon-carbon double bond breaks to give me a carbon-carbon single bond, right? And my hydrogen is going to add to carbon number one based on Markovnikov rule, right? Remember, Markovnikov rule states that the hydrogen will add to the carbon that share the double bond that has the most hydrogen. Carbon 1 has two hydrogens. Carbon number 2 only has one hydrogen directly bonded to it. Directly bonded here is a CH3. These three hydrogens are on carbon 3. So your hydrogen, when the double bond breaks, is going to add to carbon number 1. So let's translate over in our product what this first arrow means, right? Now, let's draw back my three carbons. I didn't lose them. Please put them back, right? So this is carbon 3, carbon 2, carbon 1, right? On carbon 3, I still have three hydrogens. I didn't lose them, so I need to put my three hydrogens back. On carbon 2, I have one hydrogen. Please put the one hydrogen back. On carbon 2, on carbon 1, I'm sorry, I have two hydrogens. Let's put them back. When you don't lose things, you can't just magically not put them back, okay? We don't do that in chemistry. So remember, we said that this arrow means the double bond breaks. So if you notice, I have a single bond between carbon 1 and carbon 2. That's the first thing. That double bond breaks, leaving you with a single bond. And this bond is used to make the bond between carbon number one and my red hydrogen. So on carbon one, we're going to have our hydrogen, right? So this arrow means that this hydrogen made a bond with carbon one based on Markovnikov rule. Now remember, before I go to what happens here, let's talk about carbon two. Carbon number two has only three bonds. It doesn't have a full octet. It lacks those 8 electrons. It only has 6, 2, 4, 6. So it has a positive charge. We have generated a secondary carbocation, right? And I know it's secondary because, as usual, find the carbon with the positive charge and then look how many carbons are directly bonded to it. Directly bonded to it is carbon 1. Directly bonded to it is carbon 3. This is directly bonded, but it's not a carbon. We're counting the number of carbons that are directly bonded. It's 2, so it's a secondary carbocation. Let's talk about what happens in this part. So this arrow means the hydrogen goes with carbon 1. Hydrogen cannot have two bonds, right? Remember, the hydrogen is making a bond with carbon 1. We did it here, okay? I have to break the bond between the oxygen and the hydrogen, which shows that the hydrogen left, right? So remember how we show that a bond is being broken between two atoms. It means that this oxygen will have to steal these 2 electrons. So to show that this hydrogen went about its business with carbon 1, you have to show it breaking away from the relationship it had being shared between hydrogen and oxygen, okay? Because the hydrogen can't have two bonds. If I didn't break it away, this is what you would end up with. Hydrogen, you would end up with plus H, H. We don't do that. The hydrogen can't have two bonds to it. It can only have one. So you have to show that it broke away. And how do you do that? You show that by basically saying that oxygen steal the 2 electrons that make up this bond. It's no longer being shared between the oxygen and the hydrogen. Or you could just follow the arrow, right? If I'm stealing this hydrogen and I draw an arrow from this bond onto an atom. Remember, when you draw an arrow from a bond onto an atom, it means the 2 electrons that make up this bond is now on the oxygen, no longer being shared. So we end up with, you have your oxygen. So put your oxygen back with its 2 hydrogens, right? And its lone pair. I didn't use these lone pair for anything, so I need you to put them back. But the question is now, do we have a positive charge? And remember, these 2 electrons are now on the oxygen. So instead of one lone pair, I now have two, right? So this is water. This is water. And water doesn't have a charge. If you didn't realize that, this is how you figure that out. The 2 electrons you put on here quenches the positive charge that's on it. So it's neutral, okay? And if you think about it, here the 2 electrons were being shared between the oxygen and the hydrogen. That's no longer happening. So I'm putting the 2 electrons here, giving it negativity, and I have a positive on it. I'm going to kill the positive charge, becomes neutral. That's step number 1. So in step 1, by the way, this is the slowest step of the reaction, which is your rate determining step, right? So that's step 1. We generated our carbocation and we generated some water, okay? In step 2, in step number 2, we're gonna make a new bond between a nucleophile. Most of your reactions is nucleophilic, electrophilic relationship happening. We're gonna make our reaction between a nucleophile, the water, but in this case, it's the water that you were given in the beginning, your blue water. So your blue water finally comes into play. We're going to make a bond between your nucleophile, the water, and the carbocation. So the carbocation will now act as your electrophile, right? And we all know why. Electrophiles love electrons, so they're sinks, okay? So let's do that in step number 2. Always remember, in your mechanisms, you have to redraw the product that you get. This is what you have, right? So redraw this. Sorry, redraw the carbocation. This comes in play in step 3 because this came from our acid. This water here came from our acid, right? So it doesn't up, that water isn't what reacts in the second step. So redraw the carbocation. Right, let's redraw our carbocation. And let me take it all the way over here so I have more space. So let's redraw our carbocation. All right, carbon 1, 2, 3. So we redraw our carbocation. Carbocation is now going to react with the water that they gave us in the beginning of the reaction. It's important that you see that this is the water that is taking place in this step. So we're going to react it with water. So the usual, right? Remember, your reaction is you're looking for your nucleophile and you're looking for your electrophile. Every time you're given two reactants, find the electrophile, find the nucleophile, right? In this reaction, the only thing here that could act as a source is this. This is the only thing that is rich in electrons, that have some electron that could give and will act as your source. This is your sink, right? This is the only thing here that lacks electron and is ready to receive it, right? So this will be your electrophile, right? Or your sink. Sink, as in exactly what it means, is it lacks electrons. And you always draw your arrow from your source to your sink. And what this arrow means is that the lone pair makes a bond with carbon number 2. Okay, so let's draw that on the other side of this reaction. So let's draw 3 carbons. We didn't lose any of them, right? So those are my 3 carbons. Carbon 3, carbon 2, carbon 1. Put your hydrogens back. My carbon 2 has a hydrogen. Carbon, this hydrogen is red, I'm sorry. It came from the acid, that's all we're showing. Then remember that these 2 electrons are going to make a bond with the carbon, okay? So let's make a bond. So that's the bond. So oxygen, so water, so the oxygen use the 2 electrons and make a bond with carbon 2, right? Which means that oxygen now only has these lone pairs because I didn't use them up. And we didn't do anything to the oxygens. Please, the hydrogens, I'm sorry, please put them back. Now, this oxygen has a positive charge. And if you didn't see how, let's talk about it. I have a lone pair on the oxygen here. Yes? When there are a lone pair on the oxygen, when you have a lone pair on the oxygen, it's not being shared. It belongs to oxygen only. But when I use these lone pairs and make a bond, guess what? The electrons are now being shared between the carbon and the oxygen. So I'm sharing my electrons. They're not sitting on the oxygen anymore. They're now being shared. Okay, so here I have two electrons to myself. I am very negative because electrons are negative, but hey, now I'm sharing some of the negativity with carbon. So it generates a positive charge, right? So this couldn't be negative. It had to be positive. And remember, I already taught you, if you have forgotten, maybe you should go back and watch. Oxygen will be neutral when it has two bonds and two lone pairs. Anything else, it must have a charge. Here is three bonds and one lone pair, so there has to be a charge here. This is what we call an oxonium ion because it has that positive charge. It's an oxygen with a positive charge. This step, right, is fast, and I know you know why because I've been singing this whole time. Once you form an intermediate, it's very reactive, so it reacts almost immediately, right, to give you this. That's why this is fast. This is slow. We don't have any intermediates here, right? But remember, this carbon has an empty p orbitals and it's happy and ready and just waiting. Give me two electrons, okay? So that's step two. Let's look at what happened in step number three of this reaction. In step three, right, our oxonium ion is going to react with the water molecule that we generated in the first step. Because remember, your catalyst needs to be regenerated. So we're going to regenerate the catalyst in step three. And in step three, what you end up with is us losing a proton. So we get deprotonation of the oxonium ion. Okay? So let's call step three proton transfer or take away a proton. Or proton removal, whichever one works for you. So let's redraw our oxonium ion. So three carbons, hydrogen, 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 hydrogen. My then okay, let me put the lone pairs back at the bottom. We're gonna put these hydrogens back here. And we're going to react this, like I said, with the water generated in the first step. That's our red water, right? We're going to react it with our red water. So your red water comes in at the final step to regenerate your acid, your catalyst. So remember the catalyst in a reaction. So this proves it's true, you know, that a catalyst, it doesn't get used up. It's regenerated in this final step of the reaction. So our usual, you're looking for a source and you're looking for a sink. Your source in this reaction is going to be your water. There's nothing else in this reaction that could act as a source. So your source is you'll use the lone pairs of the water to make a bond with this hydrogen, right? This is the only thing here that could act as a sink. You can either use this hydrogen or this one, it doesn't matter. So you draw an arrow from here, source to sink. People notice every single time, every time. Every time I draw a bond from a lone pair to a hydrogen, right, I'm making a bond with the hydrogen. So I must break the bond between the hydrogen and whichever atom it's bonded to. I have to because the hydrogen can only make one bond. So you'll take these two electrons and you put it on your oxygen. Let me put these lone pairs somewhere else so you can see that they're still there. Here we go. So always realize that you have to break this bond. Everything in organic is a pattern, right? And it's like the curved arrows, they flow, right? So let's Let's write over here what results from these arrows. So this arrow is basically telling me that the lone pair from the oxygen is going to make a bond with my blue hydrogen, right? And then this one is indicating that the two electrons that is shared by the hydrogen and the oxygen, those two electrons is now they're now moved to the oxygen only. So they're no longer being shared. So let's draw this. I have three carbons, put my hydrogens back, right? Here we have our oxygen. I didn't do anything to this hydrogen, put it back. Leave my lone pairs, I didn't use them. So here, I didn't do anything to this hydrogen, put it back. Didn't do anything to my lone pair, put it back. But what I did do, right, I did move the two electrons from this bond onto the oxygen. There's no charge on here. I quench by moving the two electrons from here onto this oxygen, I quench the positive charge. Or just remember what I told you. You have an oxygen if you have two single bonds and two lone pairs, then it's new. The oxygen is neutral, right? And we're not done yet. Let's look at what the other arrow means. So this arrow means that I use this lone pair, right? And I made a bond with this hydrogen. So let's do that. So I have my oxygen. I only use up this lone pair to make a bond with that. So let's make a bond with this hydrogen. So if you notice, what we've done is that we've regenerated the catalyst. And of course, since my lone pair is now being shared, I decrease the negativity, so the charge on this is positive, right? So we have regenerated our catalyst. I'll keep this red. We have regenerated our catalyst at the end of the reaction, which makes sense, and you have made your alcohol. So I'm going to tell you this. If you understand reaction mechanism and you can see it, it makes it so much easier for you to write a product, right? If you react an alkene with water, it is going to give you an alcohol. That's another thing. You need to remember what functional groups you get when you react alkene plus water, for example, you get alcohol. If you react alkene plus HX, you're getting an alkyl halide. You have to remember those things for when you start doing like retrosynthesis, etc.